Novaya Zemlya's ice mass response to atmospheric oceanic warming. Basically, it suggests that the mass loss is greatest from marine terminating basins located along the Barents Coast. These and other studies, and they cite them, have made a range of inferences linking observations of glacier change to external forcing. And for example, this paper Carr in 2017 found a correlation between SST, SIC, sea ice concentration, and accelerated glacier retreat across Novaya Zemlya from 2000 to 2012. So they worked off of that, expanded it. Climate reanalyses reveal a clear difference in SIC, SST, SOTF anomaly trend between the Barents and Kara coast since the early 2000s. We just looked at that in figures 4 and 5. Between 03 and 18, SST, SOTF 1 to 3 studied sites increased on average by 0.1 to 0.3 Celsius per annum along the Barents Coast, while ocean temperatures remain relatively stable along the Kara Coast. During the same time period, sea ice concentration decreased at rates greater than 3% per annum off the Barents Coast compared to just 1% per annum along the Kara Coast. But it's still, along the Kara Coast, it's still decreased, except that it was at least 3 times more so along the Barents Coast. Which makes sense. The Barents Coast is getting hit with that warm Atlantic water. We also note that SIC and SST warming anomaly trends along the Barents Coast are steepest during, that's March, April, May, MAM. March, April, May, June, July, August, respectively. Along the main path of Atlantic water inflow. SOTF anomalies appear large at all depths because it's intermediate water, and rates of subsurface warming greater than 0.1 C per annum are pervasive in all seasons in the eastern Barents Sea. The sustained ocean forcing is consistent with the high frontal velocities reported for Barents Coast marine terminating outlet glaciers. In other words, the warming ocean is forcing the ice loss. Taken all together, these forcing patterns suggest that high surface melt rates in spring and summer coincide with strong ocean forcing at the calving front, forming a concomitant driver of rapid dynamic thinning along the western margins of Severny ice cap in Novaya Zemlya. Furthermore, evidence suggests persistent decadal upwelling of relatively warm subsurface ocean water through vertical Ekman transport, sometimes called vertical Ekman pumping, around Novaya Zemlya. Based on these observations, we infer that in addition to ubiquitous net surface losses, ocean forcing is a key parameter that explains A, the 59% difference in mass loss from west coast compared to east coast facing tidewater glaciers, and B, the 72% and 59% higher rates of loss from tidewater glaciers on the Barents and Kara Sea coast, respectively, compared to the land terminating. Atlantic Ocean fingerprint on Severnaya Zemlya's dynamic imbalance. The highly heterogeneous response, basically it was different all over the place, of Severnaya Zemlya's glaciers and ice caps to external forcing suggests either a more varied and complex set of control mechanisms on glacier change compared to Novaya Zemlya, or a more dramatic dynamic response to the same set of forcings. Okay. And they go through a whole bunch of possibilities, this, that, and the other thing. A net decrease in Atlantic influence over Severnaya Zemlya compared to Novaya Zemlya is evident in the less pronounced 2-meter temperature and sea ice concentration anomaly trends. In other words, the influence of the Atlantic hasn't quite made it to there yet, because it is Severnaya is east of Novaya Zemlya. Furthermore, ocean warming around Severnaya Zemlya is delayed with respect to warming in the Barents Sea, with steeper trends emerging only in the 2010s, in particular along the Laptev coast. Excuse me. The most prominent climatic signal in the vicinity of the archipelago is the persistent positive SOTF, basically that reflects the North Atlantic Intermediate Water, anomaly warming trend along the Eurasian continental slope, which affects certain locales there. Rates of upwelling along the east coast of Severnaya Zemlya have increased over the past 4 decades as a result of enhanced Ekman pumping in the Laptev Sea. We therefore infer, in line with observations elsewhere, that this long-term enhanced oceanic heat supply represents a potential control on glacier dynamics in the region. Now, this is going to be most likely coming events in the future. A sustained upward movement of relatively warm subsurface water assisted by coastal surface currents and tides may result in these warm waters reaching the fronts of some of Severnaya Zemlya's glaciers and ice caps, in particular eastern and southern basins. This all ties in to what I was saying earlier, that the warm influence of the North Atlantic Intermediate Water is working its way eastward. It's obviously influencing what's going on the Barents side around Novaya Zemlya. It's still, its influence hasn't quite reached to Severnaya Zemlya yet, but it's getting there. Okay, now they look at a coupled versus decoupled climatic forcing. Further examine the sensitivity of Russian Arctic glacier response to climatic change. They perform quantitative assessment, surface elevation, change the DH, seasonal forcing anomalies, and so on and so forth. So they looked at correlation. So they're doing some statistical analyses. Okay? They perform a regression analysis between the change in height and each of the forcing using original and the trended time series for comparison. And then the latter calculated by subtracting the linear forcing over the full length, yada, yada, yada. What it comes down to is these analyses reveal a significant link, probability is less than 0.01, between ocean forcing and change in height along Novaya Zemlya's Barents coast, with maximum values of R square, that's how well the data fits, ranging between 0.23, 0.63, 0.19, 0.41 when using detrended time series. Correlation between the change in height and a 2 meter or sea ice concentration generally weaker, which may be explained in part by high seasonal variability in the forcings. Furthermore, the statistical significance of the correlation between DH and all climate forcing decreases from west to east across the BKS, with p-values greater than 0.01 over Severnaya Zemlya. That means it was not significant. Where a consistent delay in response is not evidence. What I just said, not significant. Then they go on to say that because of the seasonal variations, interannual and so on, decadal variation, they then did some other regression analyses with the 1.5-year moving average. They apply that as a filter to tease out any signals. The smooth forcing patterns highlight a general warming trend on which are superimposed 4 to 5 year cycles during which the temperature 2 meters, sea ice concentration, sea surface temperature, the intermediate water anomalies oscillate in phase over Novaya Zemlya and increasingly out of phase when moving eastward. This overarching oscillating pattern is possibly associated with leading modes of large-scale climate variability such as the Arctic and the North Atlantic Oscillation, and I would add the Arctic Dipole. And I've done videos on that, on the AO, the NAO, the Arctic Dipole. Please check those out if you haven't done so already for an explanation of what they all do and how they impact what happens in the Arctic. So, figure 6, forcing anomalies and change in height time series, plotted for each of the 12 control areas. Novaya Zemlya, Barents is on the left, Karakos is on the middle left, Severnaya Zemlya is Kara on the middle right, Laptev on the far right. To average out short-term climatic fluctuations, DH and all forcing anomalies are represented by the 1.5 years moving mean. Right, we just discussed that. So let's take a look at the figure here. And let's see if I do a little bit of an increase here. Normalized forcings. This is DH shifted. This is probably the 1.5 year smoothing that's being shifted. And when you do so, you can see it correlates fairly well. Not perfect, but it's fairly well. But when you come over to the Severnaya Zemlya side of things, you can see why the p-value is greater than 0.1. Really does not correlate well. Is a decent correlation for Novaya Zemlya, but not for Severnaya Zemlya. And that's what they're discussing in the text. Regressions performed on each of the smooth time series confirm significant correlation between DH and all the forcing in the areas along the Barents coast of Novaya Zemlya. Figure 7, which is this guy here. We'll get to that in a moment. With R-squared values varying between 0.25 and 0.83. That's pretty decent, depending on the forcing. We report these correlations with a high level of confidence. P is less than 0.005, although we note that the fits and the statistical significance are possibly enhanced by the low-pass filtering of the time series. Basically, how they're smoothing the data and so on. The level of significance of the correlation decreases in the areas K1N through K3N along the Kara coast of Novaya Zemlya, where only basically the intermediate water exhibits a significant relationship to ice thinning. Over Severnaya Zemlya, the correspondence between different forcings and thinning rates is less clear and more variable. I would say that's more variable, right? It certainly is more variable when you look at it. And here are the different, you can look at the different colors. So here's the Kara side, the Barents side, right? And so on. But you got some decent correlations here. Now, let's look at figure 7. This is so we got p-values less than 0.005, less than 0.5. Okay, and here's your R-square. So these two is Novaya Zemlya, these two is Severnaya Zemlya. And as you can see, Novaya Zemlya tends to have better R-square values for looking at all the forcing than does Severnaya Zemlya. A couple high ones here and there, right, for sea surface temperature, and the blue dot is the SOTF2. But we got between SOTF 2 and 3, we got some good correlation, not pretty decent correlations when looking at sea surface temperature. But we can see what? The influence. This is showing a good correlation between the influence of the intermediate water and what it is doing to the ice. At least for Novaya Zemlya. We infer that changes in mass loss over Novaya Zemlya from 2010 to 2018 were modulated by a coupled atmosphere, 2 meter, to ocean, right? Sea ice concentration, sea surface temperature, intermediate water, forcing mechanism with all controls displaying a non-statutory non-stationary oscillatory forcing pattern with a 4 to 5 year periodicity and decreasing strength from west to east. They go on to say that we infer that periods of accelerated ice loss between 2011 and 2013 and after 2016 were in response to a preceding acceleration in warming during the periods 09 to 11 and 14 to 16 respectively. We argue that the Atlantic supply of oceanic heat controls frontal ablation via submarine melting and calving and drives the inland propagating dynamic imbalance of tidewater glaciers, as revealed by intense thinning over large areas at low elevation across marine terminating catchments. At the same time, receding sea ice in the eastern and northern Barents allows for heat fluxes to rise vertically through the water column and into the atmospheric boundary layer. I'm going to highlight all of that. This increases both sea and air surface temperatures locally, further enhancing sea ice loss and the already pervasive surface melt across Novaya Zemlya. There's your mechanism, folks. They have data showing this. Excuse me. They have data showing that the warm Atlantic water coming in melts the ice, and when there's no ice, diffuses right into the atmosphere. They're stating it right there. The data backs that up. Coupled atmospheric ocean forcing is less prevalent in the eastern BKS, where a more pronounced ocean stratification, again, Igor's paper of 2017, a pronounced ocean stratification impedes the propagation of vertical heat fluxes and higher sea ice concentration inhibit the efficient ocean to atmosphere heat transfer. Figure 8, which we'll get to in a moment. So basically, if you've got a strong halocline due to all the freshwater input, riverine input, maybe whatever sea ice there, the heat may not be able to get to diffuse as readily as it does elsewhere to the atmosphere. That's basically what they're saying there. And if you got the sea ice there, it could be act as a cap. Upwelling of relatively warm subsurface water with Atlantic signature is nonetheless sustained by vertical Ekman transport along the continental slope, an occurrence that is likely to have an effect on submarine melting and calving of the east-facing glacier front of Severnaya Zemlya. Okay, remember, the shelf is decreases in depth gradually until you get to the shelf break, and then the decrease in depth becomes more pronounced. That's the slope. So now you got Ekman pumping up the slope. Some of it may go onto the shelf. And that warm water will work on ice that faces it, that receives that warmth. That's what they're saying there. Hence, atmospheric oceanic forcings drove differing patterns of mass changes over the archipelago, reflecting decoupled environmental forcing. Under these conditions, low annual mean air temperatures and precipitation rates led to slight and almost ubiquitous mass gain distributed across the surface of the ice caps. Recall earlier, we saw those two stations where there was a little bit of gain in the mass there. That's what they're referring to here. So, figure 8, schematic, right? It's called a model, little diagram, a schematic illustrating heat fluxes in the BKS region. Okay, IHC is the integrated ocean heat content, right? Integrated heat content with horizontal arrows, symbolizing lateral ocean heat fluxes, vertical heat fluxes, HFV. So HFV, heat flux vertical. HFZ, heat flux horizontal. I don't know why I use Z for horizontal. Okay. cross the water column into the atmospheric boundary, leading to synchronous coupled atmospheric ocean forcing on land ice. Higher sea ice concentrations around Severnaya Zemlya decouple potential atmosphere-ocean interactions, dissociating the respective impact on land ice mass. So let's enlarge this. Okay. Novaya Zemlya, right? Severnaya Zemlya. Coupled forcing. So as more red is coupled forcing, more blue is decoupled forcing. Atlantic domain, Arctic domain. So here is horizontal heat fluxes continuing this way. Then we get vertical heat fluxes. This is the heat that goes into the atmosphere, warming, at least locally, the air above it. We know that the water here is warmer. And we can see this is the transition zone. And basically, the Atlantification hasn't quite reached Severnaya Zemlya yet. We still see some sea ice. Now, this is probably going to be, as we showed earlier, March, April, May, which is, don't forget, oceanic winter. That's when sea ice is going to be at its thickest. June, July, August is springtime. The ice is going to be thinning. When you start getting into August, September, and October, that's oceanic summer. That's when the sea ice will be at a minimum. So when when you see people saying, well, the lab tip is ice free and so on, yeah, they're looking at September, October, possibly even as early as August. Think of this as what's happening in March, April. Now, Severnaya Zemlya is kind of in between the influence of the North Atlantic water and the influence from what comes in from the Pacific through the Bering Strait on that side. That warm water is reaching over here, East Siberian. So it's sort of like it hasn't quite caught up to where we start losing this sea ice earlier in the year than what's currently taking place. But we do know by the time we get to oceanic summertime, basically late August, September, so forth, the Laptev is pretty much ice-free, as is the East Siberian. And the East Siberian is also losing its ice as well. So think of this mechanism, right? They're explaining what's coming in from the Atlantic side. Think of this mechanism being repeated for what comes in through the Pacific. The heat diffuses upward, melts the ice, and then continues to warm the air. It's just that the influence from the Pacific side, the influence from the Atlantic side hasn't quite reached Severnaya Novaya. It hasn't quite reached the Kara Sea yet. Give this some time as the influence starts working its way west to east. And what you see on this right side of this diagram here will start looking more and more like what we see over here. That is probably what's going to be coming down the road in a few years. So let's look at the summary and conclusions, and we'll wrap this up. We find that Novaya Zemlya continues to dominate sea level input in the BKS region, right? That 2.1 to 3.5 centimeter increase, with the total ice loss of that many gigatons per year, driven by similar area-specific rates of loss from both land and marine terminating glaciers. And those are the values right there. Along the Novaya Zemlya's Barents coast, both surface melt ice dynamics form a strong coupled mechanism leading to enhanced tidewater glacier mass imbalance due to dramatic thinning in the lower tidewater terminus regions. We don't see the same things. We don't see the same thing in Severnaya Zemlya. Our results reveal a clear and significant link between amplified coupled atmosphere ocean forcing and ice thinning over Novaya Zemlya with a 1.5-year delay in the response of the ice masses to the onset of forcing. That makes sense, right? And that's what we tried to show earlier in those particular figures. This linear response is particularly strong along the Barents Sea coast, where ongoing Atlantification is driving the climate dynamics and the subsequent ice mass response. Calving rates in Severnaya Zemlya are also controlled by Atlantic Ocean heat transfer, in this instance along the Eurasian continental slope, assisted by Ekman vertical transport, enabling warmer waters to reach tidewater glaciers. However, over Severnaya Zemlya, oceanic and atmospheric forcing are decoupled. So it's not coupled like it is over Novaya Zemlya. A linear relationship between ice loss and oceanic atmospheric forcing has been demonstrated in the Eurasian High Arctic. Coupled atmosphere-ocean warming feedback is currently expanding eastwards in response to the northward shift of Atlantic climate. This is a very important paper that Igor published back in 4 years ago. Sea ice decline, positive climate feedback. Our detailed temporal and spatial observation of patterns of glacial thinning suggests that this progression is already significantly impacting glacier ice cap stability in the eastern Russian Arctic, with the potential for future dynamic regime changes, enhanced mechanisms of ice loss. Our study, despite the complexity of the climate variability in the BKS sector, range of dynamic responses specific to the Russian High Arctic, our study confirms that relatively simple linear relationships are sufficient to describe regional ice-climate interactions and may be used to predict future ice loss in regions where coupled ocean-atmosphere forcing prevails. These relationships provide considerable potential for improving global sea level projections through the incorporations of parametrizations in coupled ice atmosphere ocean modeling work. This figure sums it all up. Warm Atlantic water influences the ice. You got the heat, because there's basically no ice in the Barents, so that heat then starts working on the ice, melting the ice. That's the coupled forcing. Has not quite reached over on this side to the Severnaya, hence it's decoupled. But we're starting to see the influence of the intermediate water thanks to Ekman pumping on from the slope onto the shelf that is working on eastward facing ice. Eventually, this heat is going to reach over here, and then you're going to shift this from decoupled to a coupled forcing. Combine that with water coming in from the Pacific side, and you get this. You start shifting this mechanism, what we see here, to here. So overall, what does this mean for the Russian side? The Eurasian side of the Arctic Ocean. This is going to lead to, at least on the Eurasian side of the Arctic Ocean, blue ocean events. Eventually. When you get into the Canadian side of things, or the North American side of things, areas around Greenland and within the Canadian archipelago, Ellesmere Island, that's where we still see some of the last remnants of the multi-year sea ice. That's still persisting. That'll probably be the last ice to go before there's absolutely no ice anywhere in the Arctic Ocean, during the summertime. Now, does that constitute a BOE? Well, traditionally, a BOE was defined as having less than 1 million square kilometers of ice. Well, guess what? We've already had that. If you use that definition of the BOE, we've already had BOE. But there's some people who say the BOE means no ice anywhere. And if you go by that criterion, we haven't had it. But when you look at this mechanism, heat from the Atlantic side, heat from the Barents side, all the sea ice is eventually going, at least on the Eurasian side, will be disappearing. Heat diffuses to the atmosphere, warms the ice from above. The Atlantic water starts reaching over here, onshore pumping the warming water, melts the ice from below. See the same thing in Antarctica, by the way. Warming water underneath the ice. So we're kind of getting a good idea what the mechanism is going to be. So this is all going to lead to the sea ice being lost earlier in the year, and that persistent heat will force the freeze up to occur later in the year, until eventually the Arctic Ocean will be Atlantified almost totally, with pervasive warm water preventing ice at all from forming. And that's where we're headed. The Barents Sea is already Atlantified. It's moving into the Kara. We're seeing, I guess you could say, Pacifified through the Bering. But eventually, when you look at the main flow, and I've done videos on this, go look at those videos. When you look at the main flow, when it comes in through the Fram, the flow goes to the Eurasian side. So that's going to keep bringing that warm Atlantic water, Barents, Kara, Laptev, East Siberian, and then it makes this loop around. So eventually, this warm water is going to infiltrate the entire Arctic Ocean basin. Could very well lead to BOE events. Now, I've described to you before, what's happening, why the sea ice melts earlier, why it forms later in the year. Okay? This is tying it all together. I'm now presenting to you mechanisms, presenting to you the data that these folks here have published. And this should kind of pull this all together as to what's happening in the Arctic Ocean. So, this is, as I said, I expect this to replace this eventually, and then you add in the Pacific influence. But we are losing the ice. And of course, this is all part of the Arctic amplification, and then that has implications for the planet, because what happens in the Arctic does not stay in the Arctic. Thank you for your patience. Thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.